Welcome back to LearnRite video series. I guess you are doing very well. We've been looking at the syllabus in the chemistry theory paper. We have done the first chapter and the second chapter. The second chapter, remember, we talked about reactions within the nucleus of the atom, specifically radioactivity, or someone will call it nuclear chemistry. We look at what radioactivity is, we look at half-life, look at how half-life is calculated, look at activity, and we looked at the factors that affect the stability of various radioactive elements. We looked at certain characteristics of radioactivity, specifically fusion and fission, and the importance of these two properties or these two characteristics of radioactivity. Today, we are going to look at further details of the atomic structure. Remember, the first chapter was focused on the structure of the atom. We got up to Rutherford's model of the atom, and that gave us a hint about how the atom looks like. But we really want to do an analysis of the atom and see what really the atom looks like and how it works in the way that we find various elements and substances behave in nature. So our topic as the third chapter is that further refinement of the atomic structure. And the periodic table. The periodic table is arranged based on the structure of the atom. And so when we know the true nature of the structure of an atom, we'll get to understand how the periodic table is arranged. In other words, the elements or atoms on the periodic table are arranged. And you understand why chemists pick these atoms and try to explain how each atom or element behaves in nature. Scientists, we want to understand God. We want to know why God made this earth as it is, so that we'll be able to develop, we'll be able to do more things that God allows us to do. Now, within this chapter, the first thing that we want to know is that evidence of the existence of electronic shells from emission spectra. Let's go back to the last thing that we studied under the atomic structure. We talked about Rutherford. And remember, Rutherford was the one who added some knowledge to J.J. Thomson and Dalton. J.J. Thomson discovered the electron, and Rutherford came to discover the particles within the nucleus, or Rutherford discovered the nucleus. He did not discount the fact that there were electrons in the atom. What did Rutherford say? Rutherford at that time mentioned that the atom was made up of a small nucleus which contained the neutrons and the protons. And then of course he said that around the nucleus were electrons. He said there were electrons, negatively charged, that move in circles around the nucleus. He didn't indicate how they were structured around the nucleus. He said they move in circles around the nucleus, or they move in orbits around the nucleus. We want to see how the electrons move. We want to see where the electrons actually exist, or how they exist around the nucleus and how they move. The experiments that various scientists did had to do with emission of some kind of spectrum from atoms. Let's look at this. I don't know whether you have observed this. when you have any substance that contains atoms, or any element that contains atoms, or a compound that contains atoms, the gaseous form of it, if you subject it to serious heating, what do you see? Have you watched that done before? What do you see? If you haven't, when you go home, just try this. Pick a piece of paper and burn it. You see the paper burning, and within that glow or the fire coming from the paper, you see something in there. The fire will have a range of some colors. In the same sense, if you take the gaseous form of any substance and you heat it, or you give it some strong fire, the substance glows. In other words, it gives off light as if it is burning. When you increase the energy source, the gaseous or the vapor state of that substance will burn the more. This is how scientists or chemists did, and they were able to find out what actually is in the glow or the light, and based on that they were able to determine the true structure of the atom, particularly outside the nucleus. I have this diagram here. If you have just pure white light, the light is not coming from any atom, or it's not coming from any substance or element that contains atoms in it. If you have light, that is done in your physics. If you have just white light, pure light, we call it white light, and then you throw it through a slit like this onto a prism, the light separates into its constituent colors. Every light is made up of a number of colors. So light coming from any white source that has no atom or substance or element in it, when it is diffracted, that is the scientific word. In other words, if the light is thrown onto a diffraction grating, a prism, the prism separates the constituents of that light into various colors. And I know we have seen this before. That is our common rainbow that we see when it is about to rain. You see the red color, orange, green, whatever. I think when we're in school we learn something. The various colors that we see. Why am I able to memorize all this? Because I still have it in my head. It says the colors that you see in a white ladder: red, orange, yellow, green, blue, indigo, and violet. How do we remember these things? We say read over your geography book in vacation. So I just memorizing this in my head, and I got to know these are the colors. So for any white light, just like the rainbow, the colors of the rainbow are red, orange, yellow, green, blue, indigo, and violet. So if you have pure white light and you diffract it, you throw it onto a prism that diffracts it on a detector, you are going to see the red light. This place would have been red, then yellow, orange, yellow, green, blue, and they emerge into each other. You don't see a clear cut. You will not see a very clear cut red, and then you come and see another color orange. They dovetail. They emerge into each other. The red emerges into the orange, and then it also emerges into the yellow. Look at this, red coming to orange is quite simple. This one also emerges into yellow, and then yellow into green, green into blue, and then indigo, and then what? Violet. These are the various colors of the rainbow. That is what you see when you have pure white light. But then, because atoms or substances, when it is heated, also gives light, we can also throw that light here. So that's why we have written here, light from a gas discharge tube. In other words, we have a gas in a tube, and then we are giving it some heat. If we give it heat here in the tube containing the gas will glow, give you light, and then the light is thrown through this slit onto the prism. The prism will separate the constituent colors of that light coming from the atom or the substance. What do you see? Do you also see a continuous spectrum? Range of light do they dovetail or emerge into each other like that? That is not what you see. If it's coming from an atom, or the gas that you are using contains an atom, then because there is something within the atom, you don't see it becoming continuous, red going into orange, orange into yellow, and then you see that fine range of colors called a continuous spectrum. You don't see that. You see distinct colors. You see one color here, another color here, and in between the colors you see a dark space. Another color here, another color here, another color here. You see dark spaces. So this spectrum of colors of light that we see in science, we don't call it a continuous spectrum, but we call it a line spectrum. We call it a line spectrum. So there's a difference between a continuous spectrum and a line spectrum. A line spectrum, we say, is a set of radiation of different frequencies separated from each other by a dark space. Whereas the continuous spectrum is a range of radiations of different frequencies that move from one point to the other without any break. They move from one point to the other. You will not see this clear distinction here. It is red as it comes down. I'm using this color here as my red. You see it red up to about this point, then it will be turning to yellow. And then after the yellow, you start getting maybe green. From the yellow, you get, so this is red, this will be orange, and then it will come and turn into about yellow. In other words, there isn't any distinct demarcation between the colors that you see. You have been watching the rainbow. Maybe you have not taken critical look at it. When you go back home, anytime it's about to rain and you see the rainbow, look at it critically. That kind of spectrum or range of light that we see is called a continuous spectrum. And we see that it is one that ranges, it is a range of radiations of different frequencies that pass smoothly from one point to the next, that is from one color to the next color without a break. That is a continuous spectrum. But a line spectrum is different. It's a series of lines, colored lines or radiations with different energies, and they are separated from each other by dark spaces. So that's what we have here. So this diagram is representing a spectrum coming from a light source that has been produced from a heated gas. This diagram illustrates a line spectrum, and this line spectrum is only obtained when gaseous substances are heated to a high degree, and the light that comes off is thrown on a prism, and the prism shows the different color, the different lines with the different colors. So forgive me, I only have these blue colors, but ideally this color, that is why I've labeled them. This is color 1, this is color 2, this is color 3, this is color 4, and then we have all range of colors there. It means that we have different colors. So for any gaseous substance, for any substance that contains a gas, means that it contains an atom. When it is subjected to this experiment, you get a phenomenon like this. A spectrum, a range of colors with different radiations, different frequencies, and the colors are different. Why is it so? Why is the color coming from, the light colors coming from a gaseous atom showing this phenomenon? Remember, when we go back to Rutherford's experiment again, it says that the electrons move in orbits around the nucleus. The reason why when the atom is heated, the gaseous atom is heated, it gives us those different colors in terms of the lines, is that, let's give credit to a Danish scientist called Niels Bohr. he gave an explanation to this. Why should you see these colors? He said that, Bohr explained that because there are electrons in there, electrons are moving. When you give that electron that heat, that energy, what happens is that the electrons will gain that energy, or they become agitated, and so they move around. They move up and down, and as they move, they can emit some of the energy. And once the energy is emitted, or radiation is emitted, it is seen by the naked eye as scarlet. So assuming it moves from one level to another, that one it will gain energy. But when it moves from a high level to a lower level, it emits some radiations or energy, and that radiation is seen by the naked eye as the color. And so if this light is coming from any source with that atom, which means that it will not contain electrons, then you see the continuous spectrum. But where you have the light being diffracted onto the detector, because there are electrons in, or we say there are electrons around the nucleus, the electrons will gain the heat that we are supplying here, and that causes some movement of the electrons, and as they move, they emit radiations, and the radiations are what we see as the various colors. These radiations are separated with dark spaces. It tells us that some of the radiations are of higher energies than others. Those that are lower here have lower energies, and those that are towards where we have the end of the spectrum have higher energies. These are the explanations that Niels Bohr gave to the whole world for us to understand why electrons or atoms with electrons in them behave this way. Now, another explanation that Bohr gave is that, look at this space. It is bigger than this space, and this is bigger than this space. That is bigger than this space. So as we go, the spaces which represent different energy levels become closer. What does that indicate? It tells us something. The first point is that the set of lines converging represent transition from one energy level to another. This set of lines. And as we go, they become closer and closer. Each of these lines here represent a certain energy level. And that is why when the energy or the heat is applied to the gaseous substance, the electrons in there that gain electrons, that gain the energy, will of course emit some lines. And in the experiment, Bohr observed that the lines here do not appear at the same time. He observed that the lines there do not appear at the same time. The lines were appearing as and when the heat was increased. If you increase the heat, maybe one or two lines appear. And as you increase the heat the more, then another line appears. What did he draw from that? He concluded from that, of course, the lines here, which represent every specific energy, has a certain, the lines here that has different colors represent each specific energy. And therefore, the electrons that will exist in these lines here will have that same kind of energy level. If an electron in the atom has this energy level, not until you supply that equivalent amount of energy, the shell will not appear, so you may not see that electron. So this is the explanation to the whole thing. Let's see what we can do, or what deductions we can make from it. First, Bohr observed that the set of lines that are converging in here represent the transition from one energy level to another. What conclusion did he make from that? It means that around the nucleus there are specific energy levels, or the specific orbits in which electrons reside. The electron in this line here, which is one energy level, which he called later as a shell or an orbit, has this energy level. The nucleus is somewhere here, and so that's closest to the nucleus. Going up here, this is a second energy level. The second color represents the second energy level. And so any electron that is here, that is giving us, or that is glowing from here for it to see that line, means that there are some electrons that are also existing in this line. And the third, we also have electrons that are also existing in that transition level. the electron here has higher energy than the electron in the second level, which also has a higher energy than the electron in the first level. The second observation, the separation between energy levels decreases as we move towards a higher energy levels. Look at it, the separation, it decreases. The space between this and that is small. This one is bigger than this, and this is bigger than this, and this is bigger than. As you get to the top here, you see that they're almost becoming one line. Then the third one, there are also different lines of colors. Like I said, this is a different color, this is a different color, that is a different color, and that is a different color. Why are they different? It simply tells us that we have different transition states or different energy levels within the atom. I think I've mentioned that several times. And so electrons that come together to give us this first color are not the same as the electrons that also give us the second color, and they are also not the same as the electrons in the third color. This is an experiment that was done to illustrate that if you have it illustrates that if you have the nucleus of the atom like this, the orbits moving around it exist in this form. And so, from the second point, if the nucleus is in the middle here, the energy level of any electron will depend on the radius of that particular line. Each circle that we have drawn here represents one particular line. So in this case, if I want to relate this line here to the diagram, I'll relate it to this line. And then my second orbit can be related to the second line. My third orbit here can be related to the third line. Why? Because from the nucleus, as you go out of the nucleus, electrons have higher energies. They must have higher energies to exist in those orbits or transition state or shells. So it is from here that Niels Bohr came out with his structure of the atom. Nucleus and protons here. Nucleus positively charged. The electrons exist in this orbit, which have specific energy levels. So an electron in the first energy level cannot go to the second energy level. If you want to do that, you have to attract that energy difference between this and that. And we say the atom we say the electron absorbs energy. And when it happens that way, we say the electron is excited. If it moves from here to here, it must gain this difference in energy. That is another excited state of the electron. But an electron here may not be stable and will struggle to stay there. It can easily fall back to this level. And when it does that, it will have to give off that energy. An electron in its original energy level state is called the ground state. It is called the ground state of the electron. It is called the ground state of the electron. Basically, this is what Niels Bohr did and gave us the structure of the atom. But even that, he didn't end there. He didn't end there. After looking at this atomic spectra, of course, let me say that it is unique with every atom. If you take hydrogen and you heat it past its light through this, the spectrum you are going to see here is different from helium. And we are going to see another different spectrum from that of lithium, beryllium, and so on. So, emission from atomic spectra is one of the means by which we are able to separate or identify various atoms from others. Each one has a unique spectra. And so once you know the spectrum of an atom, if you know that, oh, this is a gaseous atom, you don't know what atom it is, just heat it, let it pass through a prism, get the structure, and you go and refer to books and you know that this is the atom. So atomic spectra is also used to differentiate between various atoms of elements. They are unique. The atomic spectrum of hydrogen is different from that of carbon, which is different from that of sodium or whatever. I'm sure within the pictures, some of them will be shown to you. Our animation will show you a number of atoms with their emission spectra. Our video will show you this, and you see how nice they look like. We cannot show it on the board. We cannot draw it on the board. But ideally, this is what happens. I'm not ending here. Come with me with some shortcomings that Bohr identified, even with this structure. He identified some shortcomings with this. This was done by the general scientific community. And after studying it critically, Bohr came back. He provided the explanation, all right, but later he came back to criticize it and did some correction. In our next video, we'll be discussing Bohr's atomic theory. Come with me on that video. Thank you.